Welcome to the lectures on fundamentals of MIMO wireless communications. We are currently exploring diversity again. We have seen the selection combining method. Now we take a look at the next combining method known as maximal ratio combining. In maximal ratio combining, what we have is again there is a single transmit antenna at the source. There is a single transmit antenna at the source, and there are multiple receive antennas at the receiver, and these lines, these different antenna lines, they would go to the combiner and there will be an output. So in each of the combiner branches there would be some weighing by, let's say, alpha 1, alpha 2 up to alpha MR. So these will be the different weight factors that would be given, and at the receiver there would be some kind of combining. So previously there was a switch and that was going through in the selection combining, but now we don't have a switch, we have a weight, and after the weight there is some kind of addition and it goes through. So this is the different method of combining, and we would term it the maximal ratio combining, also referred to as MRC. So this is the common name, MRC is the common name for this, and typically the diagram that was drawn, X is transmitted over the channel which is having coefficient H, received through one antenna, weighed by a certain weight factor, the second antenna again weighed by a certain weight factor, and so on up to MR, weighed by MR, and then there is some processing at the receiver, and then what you get is the output Y. So the output Y can be written as sum of I equals to 1 to MR. You could also write it as M for simplicity in this particular case, is alpha I times HI, the ith link, H1, H2, HMR, times X, X is transmitted, plus WI. WI is the noise due to that particular branch. So this weight factor is getting multiplied with whatever is received. For selection combining, the combining was done by I star is equal to argmax of gamma I, or argmax of mod HI squared for I equals to 1 to up to MR. This is what we did for selection combining. But for maximal ratio combining, that is MRC, we combine in a way from which this name derived is we put the weight corresponding to the strength of each of the branch, so that overall SNR is maximized at the receiver. So in this case what is done is alpha I is set equals to HI conjugate, or rather very precisely this is what you are going to find in typical books, where they give you this particular expression which is useful for BPSK or QPSK modulation. But if you are doing higher order modulation, one has to choose alpha I as HI conjugate divided by square root of sum over k h k squared. So basically it's a normalized coefficient. We do this normalization so that at the output we get the values which can be easily decoded. So when you are doing simulations, or when you are having an actual receiver, this is what you have to use, but when you are doing error probability analysis, you could do sufficiently with this for QPSK, because the SNR calculation remains the same when we do either of these two things. So if we get back to Y, the received signal Y is equal to I equals 1 to M. We are going to write M instead of MR, alpha I HIX plus WI. WI is additive white Gaussian noise. This is the channel coefficient. This is Rayleigh faded. You can assume it to be Rayleigh faded, but it can be any general distribution, which is equal to, since alpha is equal to HI conjugate, what we have is HI squared sum over I times X plus HI conjugate W. Now this you could also write it as, look at this, x times I equals 1 to m mod of hi squared plus hi conjugate w. So this is the received signal. So at the receiver, what we have is sum of all the coefficients of the channel squared. So that means each of the channel gain is getting weighed, or when we are adding up the signal, we are basically weighing it by the corresponding channel strength. In the previous case, there would have been only one channel gain, but here we are getting addition over all possible channel links that we have. So compared to selection combining, in selection, although we had all these branches, one was taking only one of these and we were dropping the signal from the other branches. But what is being done over here, all the branches are being used, but it is used in such a way that you maximize the signal to noise ratio. Now if you look at it, we are putting the weight of the branch corresponding to the strength of the branch compared to the other branches. So it's basically the ratio of the strength of that branch over the total signal strength. The advantage of this is, if some of the branch is good, you are putting more weight to that. If one of the branch is weak, you are putting less weight to that, because the error probability of this branch will be better than error probability of that branch. But I am not leaving out any branch, I am taking it but simply putting less weight to it, and the weight is being made proportional to the channel strength. So following this, if one has to calculate the signal to noise ratio from this, one would get E of x squared by E of w squared. That means the x, E of x squared by E of w squared, but at the denominator you are going to get another term, that is sum over hi mod squared, and in the numerator you are going to get a square of this term, that is sum over hi mod squared whole squared, because you are basically collecting, sorry, here is the sum of I equals 1 to m, here a sum of I equals 1 to m. So when we are calculating the energy, we are calculating basically E of, you have to do E of hi w conjugate sum over I times, let us say, k hk w I conjugate, because the conjugate of each, this is what is going to give me the power. So since hi hk are independent, so we will assume independent, that is E of hi hk equals to 0 if I is not equal to k, and is equal to 1 if I is equal to k. So that is the relationship. And again for w, E of wi wj is equal to 0 if I is not equal to j, and is equal to sigma squared w for I is equal to j. So this is the assumption that we make over here. So going by that, the power is going to be added up only when hi is equal to hk, that means I is equal to k, and since this is a function of h, this is dependent on h, we do not actually operate the E on h, so this particular part does not take into effect, only this comes into effect. So we have hi hk part, and since wi wj, E of wi wj is equal to 0 for I not equal to j, we basically have sum over I mod hi squared w and an expectation operator, this E comes inside, w squared wi squared, so E of w squared times this summation, that is the expression that we have over here. And in the numerator, in a similar manner, we have the square of this. So if you evaluate this, the SNR expression that one would get would turn out to be, the SNR that one would expect would turn out to be E of x squared by E of w squared times sum of I equals 1 to m mod of hi squared. So that means this is the gamma bar that we are getting. So the average power as in the AWGN channel case times the sum over the channel strength over all the channels. In case of selection combining, there was only one, here we have added up all the channel strength. And if we are looking at gamma m, so basically this is gamma m, the combined due to MRC. Okay, so I could write it as E of x squared by E of w squared times h1 squared plus E of x squared by E of w squared times h2 squared plus E of x squared by E of w squared times h3 squared mod, of course, up to E of x squared by E of w squared times hm mod squared. So this is basically gamma I, gamma 1, this is gamma 2, gamma 3 up to gamma m. So what we can write, this is equal to sum over gamma I equals 1 to m, meaning that the SNR that is achieved at the end of the combining is the sum of the SNR of the individual branches. So gamma 1 is the SNR of the first branch, gamma 2 is the SNR of the second branch, gamma 3 SNR of the third branch, and gamma m is the SNR of the mth branch or mrth branch. So by this particular method, one is able to add all the SNRs for the different branches. Now again, if we look at this, this particular one for Rayleigh distribution is chi-square distributed with 2 degrees of freedom. If there are m such terms, so basically it's a chi-square distributed with 2m degrees of freedom, and one could write P of gamma m is equal to gamma m raised to the power of m minus 1 e to the power of minus gamma m by gamma bar divided by gamma bar raised to the power of m by factorial m minus 1 for gamma m greater than or equal to 0, where gamma bar is the average SNR of each branch. That means expected value of gamma I is equal to gamma bar. So this way what we have seen is we have the combined SNR as sum of all the SNRs, and if you want to calculate gamma m bar, the expected value, this will be expected value of sum over gamma I, which would be since all of these are independent, we have assumed them to be independent, it would be sum over E of gamma I, which would be sum over gamma bar I equals to 1 to m. So that essentially turns out to be m times gamma bar. So what we are seeing is that the average SNR has become m times the SNR of one of the branches. In case of selection combining, just to compare, it was gamma bar and k equals 1 to capital M 1 by k. This is how it was growing, but here there is linear increase in the SNR because of MRC combining. So this is the best possible increase in SNR that you can have, and hence this particular technique is quite famous in terms of combining. So this particular technique, which is known as the maximal ratio combining, it puts weights onto each of the branches, and the weights are proportional to the channel strength, and in combining it actually uses the H conjugate, so that when it gets multiplied we get mod H squared along with this particular term, and this leads to the situation when we try to calculate the SNR, we get the sum of SNR of the individual branches, yielding that gamma m is equal to sum of all the SNRs. The average SNR hence is m times the average SNR of any one of the branches. So this is a huge potential gain that we are having over here. So if we go back to some of the previous pictures that we had drawn, yeah, let's take not this, yeah. If we take any of these pictures which could be helpful. So here we were always writing the crest, but if we now take the maximal ratio combining in this particular figure, the curve would be this signal plus the green signal plus the black signal. So it will be somewhere here, and I will draw it arbitrarily, but it is higher. All I mean to say that at this point it was just the blue, but now it will be this blue plus this green plus this black, and so the signal strength would be there. It will be higher than that, and the average SNR if it is here for all the branches, the combined average SNR would be somewhere there, which is, in this case, it is 3 times the gamma bar of each of these of the SNRs, right. So this is very interesting result that we have got, and the next very interesting thing that we need to calculate is the probability of error. We have already made the assumption that for this particular course one has to do digital communication as a prerequisite. That means it is expected that you have done some basic work in terms of error probability calculations. So we are not going to derive the error probability for additive white Gaussian noise in this particular course, because that would be unnecessarily getting into some details. So we will assume the expression for error probability for certain constellations, using which we can derive the error probability in these particular cases. Again, a reminder, like the one we did in the previous case, that if you have error probability expression in AWGN, that means when the signal strength is fixed, you have a fixed value of SNR. Whereas in this particular case, where your received signal y is hi times x plus wi, and then we do certain processing here. So it is already variable, and the SNR, that is gamma I, that I get is random. So therefore the probability of error is also random, and hence we would be interested in calculating average probability of error. So we have told earlier in the previous discussion on selection combining how to calculate probability of error for average probability of error. We will use the same technique using the density function that we have derived to calculate the average probability of error in case of MRC, and that will give us some good insights into the performance. So proceeding further, for BPSK or QPSK, you could say that okay, before the error probability is Q function of root of 2 times the SNR. So in this case, the combined SNR's PDF turns out to be gamma raised to the power of m minus 1 e to the power of minus gamma by gamma bar raised to the power of m minus 1 factorial for gamma greater than or equal to 0. Now this is true because gamma is E of x squared by E w squared multiplied by mod h squared. Now mod h squared is greater than 0, E x squared is greater than 0, E w I squared is greater than 0. So all are greater than or equal to 0. So we have this gamma to be greater than or equal to 0, and if one has to calculate PB bar, that is average bit error rate, one would integrate from 0 to infinity d gamma p gamma because of gamma m MRC, right, the error probability at a particular SNR. So what is meant by this is this function, this expression gives the probability of error when SNR is this, and we are averaging it using this p gamma because the probability of the SNR being a certain value is given by p gamma d gamma, and we are saying that gamma ranges from 0 to infinity. In this whole range of values, we are going to get the average PB. This expression is a bit cumbersome. If we define G to be square root of gamma bar, gamma 1 minus 1 plus gamma bar, we are going to get in a term which is pretty complex looking expression, m equals 0 to m minus 1 combinatorial of m minus 1 plus m 1 plus g by 2 raised to the power of m. So this gives the average probability of error for MRC combining. Now this way to calculate the probability of error is not so straightforward, but there are other techniques by which we can do it. So let us take one particular method of doing the error probability calculation. In general, the probability of symbol error, I am talking about a general expression for probability of symbol error, can be approximated as alpha m q function of square root of beta m times gamma, the particular gamma that we are using. So this is the probability of error expression for a particular modulation. Let's take rectangular QAM modulation depending upon the size of m. So this alpha m is not the m that we are using for MIMO communications. This is different. This m is the same as this related to the modulation. This m is indicating the modulation order. This is the modulation order. So please don't get confused with this alpha m and beta m. So by varying these coefficients, different size of m could be used, like one could be QPSK, another could be 16 QAM, or any such thing. Depending upon each, here alpha m and beta m would be different, here alpha m and beta m would be different. So we have to be careful with that. We will use the Chernoff bound. So by the Chernoff bound, we have q of x can be said to be less than or equal to e to the power of minus x squared by 2. This is an approximation that we can use, but the end result is, if we use this particular method, the answers that we are going to get out of this are pretty nice. So we can get good results out of this. So that's why we will be using these approximations, and they are not very wrong. They hold quite well. So we'll proceed with this particular expression. So we can say that PS is equal to alpha m times q of square root of beta m times gamma. In this case, it is gamma MRC. So this is less than or equal to alpha m e to the power of minus beta m gamma m RC by 2. So this is the expression that we are using. The Chernoff bound we are applying here. Now gamma MRC we will be using. So that is basically, this is equal to alpha m e to the power of minus beta m by 2 times sum over I equals to 1 to, let us use MR, indicating MR number of received branches, gamma I. So this is the particular expression that we need to use. Remember that we could also write it as this one. So basically PS is less than or equal to alpha m e to the power of minus beta m by 2. Instead of writing gamma I, we have I equals 1 to MR mod of HI squared times ES by N naught, or PS by sigma squared omega. This could also be written as rho. This could also be written as rho or one could also write this as alpha m e to the power of minus beta m by 2 times gamma bar times sum of HI squared I equals 1 to MR. So one could write this as PS is less than or equal to this thing, and so this as a function of this is a function of H. So it's a function of H vector. That means all the channel coefficients in case of MRC. That means these channel coefficients. So it's conditioned on these particular channel coefficients. So that's the whole vector that it is dependent upon. So what we are interested to find at this stage is PS bar. So if we have to find PS bar, what we need to do is we have to take the expectation of this over this particular thing. So if we look at this mod of, if we take this expression I equals to 1 to MR sum HI squared, for MRC this we could as good as write it as HF squared, the Frobenius norm of H, because it is contains the sum of square of all the channel coefficients. So this is that we have here, and that's very interesting. So PS we could write it as alpha m e to the power of minus beta m gamma bar by 2 HF squared. Now this is going to turn handy. So if we have to take the expectation of this, so remember E of e to the power of minus nu hf squared is given by this we had derived earlier, this particular thing we had derived earlier is given by the product of I equals to 1 to mr. Look at this, in our case we have mr, in the previous case we had mr empty when h was MIMO, but in this case there is one input, multiple outputs, it's a vector and mr number of contents in it. So the R matrix, that means the covariance matrix, is of dimension mr cross mr. So this goes to mr, otherwise it would have gone to mr empty. 1 plus nu times lambda I of R. R is the covariance matrix of vec Hermitian. R comes from expectation of vec of H times vec of H Hermitian. So this is what we have to use over here. So nu in our case is basically beta m gamma bar by 2. That's what we have to use. In case of identity, that means in case of H being independent, that means when H i's are all independent, if I do this operation, vec of H would be H1 H2 up to H mr times H1 H2 up to H mr, of course conjugate, and then an E operation. So what we are going to get is H11 squared, H1 H2 conjugate, and so on and so forth. So basically the diagonal would be H11 squared, H2 squared, H3 squared, and Hmr squared, whereas cross diagonal elements would be cross terms. For uncorrelated or independent case, E of H1 H2 conjugate is 0, and so are other coefficients except for E of Hi squared. So that means this would turn out to be E of H squared times an identity matrix of size mr, and this is equal to 1. So basically the eigenvalues of them would be 1. So basically lambda i's are 1. So in our case we can apply this. So basically when I take expected value of PS, it's basically expected value of this over HF. So that we could write it as alpha m, and then this one pi of I equals to 1 to mr, 1 by 1 plus beta m gamma bar by 2. So this particular expression, now if we look at it, all this is the same. So this you could also write it as alpha m times 1 by 1 plus beta m gamma bar by 2 raised to the power of m, and we could proceed further. That means we are assuming that all gamma I bars are gamma bar. That means the average received strength in all of the branches are the same. That is, we have made the assumption gamma I bar is equal to gamma bar, and if we assume that gamma bar is pretty large, that means for large SNR approximation we can say that expected value of PS or PS bar, or probability of symbol error, we could approximate it as alpha m, we are writing the approximate expression, times beta m. We are saying this is very large, that means it is larger compared to 1, gamma bar divided by 2 raised to the power of minus m. What we can compare this is, if we have m is equal to 1, that means if mr is equal to 1, there is only one branch, we would have alpha m divided by beta m gamma bar by 2. That means it is proportional to gamma bar raised to the power of minus 1, and which is true for a seesaw case. So what we are seeing from this expression, because we made certain approximation, the first one being the Chernoff bound that we made over here, and second thing that we used is this expected value of or the MGF, the moment generating function of Frobenius norm of H, that we have used over here, that is helping us to get this particular expression. So what we are seeing from seesaw, where it was proportional to the average probability of error, it is proportional to the inverse of average signal strength. Now it is instead proportional to, in case of MRC, is roughly we can say it is inversely proportional to the average signal strength raised to the power of minus mr. That means as MR grows, the probability of error decreases, and the order by which it decreases is given by MR, which is the number of received antenna branches. And we will see later that this exponent is known as the diversity order. So, in summary, what we see is, because of this kind of combining, the probability of error expression which is inversely proportional to the average SNR raised to the power of 1, or inversely proportional to the average SNR. What we see, it is now inversely proportional to the average SNR raised to the power of MR, that means number of receive antennas. So, that means if probability of error previously was something like this in the dB in the log scale, now the probability of error at a certain value would be much lower at that particular SNR, and that value would be dictated by this particular term. We will see more details of this particular expression in the following lecture, in which we are going to analyze the impact of M, and we will see what is meant by coding gain and diversity gain in more details. Thanks.